much. So hi everyone. It's a pleasure for me to be here. My name is Kezia Devadasan. I am a first-year PhD student at the University of Victoria in Canada. My presentation today is going to be about the role of abstraction or abstract thinking, which I will soon define in introductory programming. This study actually took place in 2021 at the end of my undergraduate degree, where I was supervised by Dr. Selena Berg, also from the University of Victoria, and Dr. Daniela Damian, who is now my PhD supervisor. So the problem that we initially started with was that first-year computer science courses have high failure rates. Furthermore, students appear to describe foundational computer science topics, even such as object-oriented programming, as quote-unquote arduous, hard to understand, and difficult. So we were wondering where this perception of first-year computer science being difficult comes from. And this was especially problematic because it seems that first-year science courses in general seem to have this perception that they're difficult. I'm sure many of us have been there with struggling through first-year chemistry and physics. At least I have. But it seems that the perception around computer science is a little bit different. So other science courses, students appear to think that, okay, if I sit down and I really work at this, I can get through this. But for some reason, there seems to be more of a mental block when it comes to computer science courses, where a lot of students are really just convinced that computer science is too difficult for them and they're not capable of learning it. So this problem has quite a few severe consequences. The first, as I've already mentioned, and is corroborated by a study by Watson in 2014, is that students struggling in a first-year computer science course have the impression that the rest of the degree is going to be impossible. So they truly believe after the first one or two courses that computer science is just too difficult for them to learn and that they're never going to be able to get a degree or succeed in this field, and so they choose to leave. And this continues to be problematic for post-secondary institutions because many universities are trying to increase the retention of students in their computer science programs. But what is currently happening might actually be the opposite. And this is especially problematic for students who are already at a higher predisposition of leaving computer science. So this might be female students or students of lower socioeconomic status, so on and so forth. So the goal of this research was actually to find other avenues in which we could make introductory computer science more approachable to students. That was our initial goal. And we settled on kind of a left field topic of abstraction. So I'm sure many of you in the audience are probably wondering, like, what is she talking about? There's many ways to make courses more approachable to students. And that's true, and many of them are being done. So the way that we settled on abstraction was actually a personal experience of mine. And I'm lucky that my supervisors were willing to explore it with me. So for a little bit of context, I took Computer Science 115, which is Foundations of Programming at the University of Victoria, and I struggled in this course. I was barely passing the exams. I was barely making it through the assignments, and I really just wasn't sure what I was not getting. And I was kind of in the same boat as many of the students are that I've just mentioned, where, we think, and I thought that computer science is, it's too difficult for me. I can't do it. If the first year course is already like this, there's really just no chance that I'm going to succeed going forward. I decided to stick it out for another term. So I barely passed that first year course. I got 60 or something like that. And then in CSE 225, which was subsequently Data Structures and Algorithms 1, I started doing really well and ended up with about an 86 in that course. But the length of time that had passed between finishing CSE 115 and starting 225 was only about 3 to 4 weeks. So I was not actually sure what I was suddenly understanding in CSE 225 that I wasn't understanding in CSE 115. And after much thought, I realized that it was maybe because I started understanding things like what makes an abstract data type abstract? Like, why is it not just a regular data type? So that's when I started speaking with my supervisors about this whole concept of abstraction. And once I had realized that it was an actual, concept or tangible thing that you could learn, it was like, it was just like an epiphany. And I was like, okay, we need to study this. So our research is then driven by three major questions. Firstly, if the level of abstraction understanding corresponds to a student's programming ability. So if a student can grasp abstraction, does it mean that they code better? Secondly, are there specific topics in the introductory curriculum that are especially dependent on a good understanding of abstraction? Or are there specific topics that, pose significant challenges for students that have deficits in abstraction understanding? And lastly, and probably most relevant to this venue, is how do students respond when abstraction is taught as an explicit learning outcome in the course? And this final research question is especially important because it's something that was not taught to my cohort. As far as I can see, it was that an instructor was never like, okay, an abstract data type is abstract because, or you're using abstraction right now because. And so students are currently expected to understand this whole concept of abstraction very implicitly, and it's never actually mentioned in instructional times. So before I can go any further, we chose to operationalize abstraction using previous work by Setter and Armoni in 2020. This paper actually used a longer definition of abstraction, but due to the scope of the project that we were doing and the length of time, we chose the three based on my supervisor's expertise that were teaching the CSC 115 course, the three parts of the definition that were most relevant to introductory programming. So the first is the black box effect, which is how can we teach students to understand like methods and functions in terms of only their inputs and outputs and without focusing and getting bogged down in the details of their implementation. The example that we give students a lot of the time is just using the print function. So, they know exactly what to pass into the print function. They know what it's going to do. Do they have any idea how it's implemented in first year computer science? Probably not. Navigating levels of abstraction. So the course that we conducted this study in was all taught all in Java. So navigating levels of abstraction was mainly about classes and figuring out where to put implementation, which class it belonged into. Can students kind of logic their way through figuring out which class is more abstract than another class? Can they order the classes in terms of levels of abstraction? And lastly, can they recognize abstraction in implementation? So they're given a lot of instructor-provided code for their assignments and lab exercises. Can they figure out the other two parts of the definition, black box effect and navigating levels of abstraction, in their assignment? And can they recognize when abstraction is being used? So what we did for this study was we explicitly taught abstraction to students. There was a two-part video series which I created that was given to students at the beginning of the semester. So the first video introduces abstraction completely outside the scope of computer science, and this was to include students that were taking their very first programming course that would not understand it anyways if I was teaching it in terms of abstract data types and whatnot. So the example that was given was you're a driver driving a car and you want to use the brakes. So you, as the driver, all you need to understand is that you put your foot on the brake pedal, the car is going to slow down. You don't need to understand like hydraulics, if there's brake fluid, if it's disc brakes, or if it's drum brakes. You just need to understand what the brakes are going to do. And such, the definition of abstraction that was given in video number 1 was to focus on ideas or slowing down the car as opposed to events, which would be like the mechanics of the brakes. The second video, what we did was we drew explicit parallels between the car braking example and the list abstract data type. So for example, we have a list that's implemented by an array-based implementation or a reference-based implementation, and that was analogous to brakes being implemented by disc brakes or drum brakes. And so the definition of abstraction in the second video was modified to focusing on behavior as opposed to implementation. And the reason that we did the second video and not combine them all in one was because we didn't want to assume that students were able to make the conceptual leap between just abstraction out there in the world where it's kind of easy to understand and suddenly in computer science. So we tried to make a longer second video to really make those parallels very explicit. So in CSC 115, the course where this was conducted, they had weekly lab exercises, which were entirely programming-based exercises, and we gave them a quiz alongside each lab that would assess their understanding of abstraction according to our operational definition, which I've just mentioned. So the quizzes were very short, very low stakes. They were each about 0.27% of their final grade, so rather insignificant. And the last question of each quiz was an open-ended question, which just asked students what was the most difficult part of this week. So we didn't want to ask them to reflect on learning abstraction or anything because we didn't want to coerce any answers about abstraction. And indeed, there were a lot of questions or responses, that were not abstraction related. And so in our analysis, we first identified a correlation between their performance on the abstraction quizzes and their performance on their grades for the relevant programming activity. And secondly, we did a qualitative analysis of the open-ended responses, asking what was the most challenging part of the week, and we sorted them out using pair coding method and until we had achieved a high inter-rater agreement. So we had basically decided whether or not that response was indeed related to a difficulty understanding abstraction specifically. So our major findings for our first and second research question. So for RQ1, we did find a correlation, which was fairly strong, between the performance on the abstraction quizzes and the actual programming exercise. So this was about 0.7, and it suggests that a good understanding of abstraction is found alongside a good ability to program. On the other hand, if a student is really struggling to understand abstraction in a certain capacity, they appear to struggle more with the actual programming exercise as well. We also found that certain topics were of special issues when it came to abstraction difficulty. So these were in particular generics, binary trees, and interfaces. So for generics, we noticed that students really struggled to understand that you could have something that represented kind of any data type. It was generic for lack of a better word, but they weren't really able to understand why that was more abstract than using a specific data type. In terms of binary trees, we noticed that the difficulty appeared to come from how a binary tree was the first visually nonlinear abstract data type that they had seen. So they struggled less with lists, but for example, a binary tree being implemented by an array-based implementation, some of the comments were like, I don't understand why a binary tree is an array. So that suggests that there is no decoupling between the implementation of the binary tree and the behavior of a binary tree, and that's really what makes it an abstract data type. And finally, interfaces was also quite problematic for students, likely because it was also one of the first activities they saw with multiple classes, and suddenly we were asking them, which is more abstract than the other. So in the activity, they had a shape interface, and a circle class and a rectangle class implemented this shape interface. And we asked them, if you were to add another method that was going to be used by rectangle and circle, where would you have to add it? And they simply missed the fact that you would have to implement it into the interface, define it in the interface. So they really did struggle with those three topics, was by far the worst. On the other hand, though, there were certain topics that seemed to not really be problematic for students at all, and most notably was exceptions. And we noticed from their responses that this seemed to be just because the concept of an exception was very similar to, like the try-catch was very similar to the if-else that they had already learned. So it didn't seem to be a big jump conceptually. And also binary search trees seem to be very, very well received. And we attributed this one to the practice effect because they had mostly ironed out all of their misunderstanding from the week prior, where they just did binary trees, which was one of the most problematic. So by the time they were just adding the search property, it was relatively straightforward for them. So most interesting, in my opinion, and I think most relevant, again, to this venue would be the findings for RQ3, which is how students respond to being taught abstraction explicitly. So it seemed that students were mostly able to understand abstraction as a general concept. The car braking example was very well received, but they still struggled to apply it to computer science concepts. So even though we were trying to make those explicit parallels, it really seemed that a lot of the times it just wasn't clear to them why a certain ADT was abstract. I have this quote here that says, "I found abstraction initially very hard to explain and the quizzes were impossible, but I watched the video with the car braking example a few times and slowly it started to make sense and the quizzes felt better." And this kind of quote is well backed up by other research, which suggests that abstraction is not a skill that's either just mastered or not mastered. There's no kind of dichotomy in the understanding of abstraction. It's something that students understand very slowly over a long time, after being exposed to many examples and going through many different types of programming exercises. And we also noticed that students seem to prefer an explicit emphasis on abstraction during instructional periods, which has actually been recommended by other researchers who have looked into this, Kopelman and Schwill, who suggest that abstraction needs to be taught explicitly because, again, as an instructor, if you're writing code in front of a bunch of students, they're not going to understand when you are using abstraction. They're going to understand it implicitly, but it makes it a lot easier for students to learn if it's being addressed. So in terms of pedagogical improvements, I've already mentioned teaching abstraction explicitly is very helpful to students. And also, Schwill presented an interesting model about teaching by concept as opposed to topics and chapters. So in this course, we did teach by topic and chapters. We taught arrays, lists, interfaces, so on and so forth, and then all the way down through hash maps. But he suggests actually teaching by concept, where a concept could be abstraction, and then you teach all of the applications of that concept. So the applications of abstraction would be the various abstract data types that you could use, binary trees, lists, etc. And finally, to use real-world concepts. So again, the car braking example was very well received by students. And when they were struggling, we noticed them kind of talking about it with each other, and they were mentioning it during the in their responses in the quizzes that we were reading. The first video that we gave them used more than one example. There was also an example of how using certain pronouns like she is an abstraction because it hides certain information. So if I say, she goes to the University of Victoria, it's more abstract than saying Casey Devadasan, a student of a computer science department, goes to University of Victoria. There's some information hiding happening there. So those are the main pedagogical improvements that we can see room for. And if I haven't convinced you yet, just the case for abstraction is quite strong in the literature. Computer scientists are, I have a quote, sorry, it says computer scientists are individuals who can rapidly change levels of abstraction, simultaneously seeing things in the large and in the small. It's also very relevant to skills all throughout the computer science degree, which it's not just relevant for learning programming, and it's not something you forget about after your first year is over. Even in third and fourth year, when we're taking theory courses and doing reductions and things like that, abstraction is extremely important because you are actually required to understand things in terms of just their inputs and their outputs. And when you understand abstraction as an explicit concept, it makes it much easier to understand what you're doing and makes students more comfortable almost ignoring pieces of information that they know they don't need. Finally, I thought this was very important, was that there's work that shows that teaching abstraction not only increases student performance, but also confidence. And this goes back to one of our initial pieces of motivation, which was that we're trying to prevent the attrition of students from computer science just because they simply think it's difficult. So if we can introduce something in the classroom which is as simple as abstraction, and it's simple for us as instructors to teach because we completely understand it, we should, because it makes them more confident and obviously, of course, helps them in their understanding. In terms of future work, there's so much that can be done in this area. Two major points would be potentially designing some kind of similar study with an independent samples model to further confirm the relevance of abstraction. And so I mean, like, having one class that is not taught abstraction explicitly and having one class that is, and having them take the same assessments and then seeing if one class does indeed perform significantly better. This was one major piece of feedback for my work, which I completely agreed with. And unfortunately, when we initially designed this study last year, we wanted to do this, but there was a few ethical concerns about giving some students in a cohort access to educational material that others could not access, and whether or not that would be fair. So that's definitely something that, if we can find a workaround to, would be really interesting to see. And also, there's lots of research about teaching abstraction with in different ways to incorporate different types of learning, because students simply don't grasp things if they're not taught in a learning style that suits them. And so there's a lot of work that would go into there. It's pretty complicated how many different variables there would be, but certainly a big place for future work that I would be very interested in looking into. So that concludes my talk for now. Thank you so much for being here, and I'm happy to answer any questions.
Let's thank our speaker both virtually and in person. I think our great student volunteer in the room is going to start passing around a microphone, but I'll start, because this is a virtual talk, with a virtual question, which is a question I've had various educators tell me. This is from Matthew Roberts. The key to learning programming is to understand the notional machine. It seems you might be putting together a case for an alternative. Do you see abstraction as a kind of opposite of a notional machine?
Potentially. I mean, I think the research into this is it's pretty new. I had a pretty hard time finding work that was exactly about abstraction and introductory programming. So a lot of the work that I had to do was seeing what was able to be generalized into the introductory programming field, I suppose. And also, I think students struggle in introductory programming for so many different reasons, and abstraction is definitely probably just one of them. It was definitely my reason, but I think I had peers for sure that were struggling just for different reasons. So I'm not sure if I can say that this is a direct alternative or anything like that, but I think it's something that we can add as a tool as instructors to be at least aware of for our students.
Great. Is there a question in the room? And if there is, it looks like there is. Please go ahead.
You can try to speak and ask them if they can hear us.
Can you hear me? Yeah. Good. Try again. It's not green. I think it might work. Good. Can you hear me, Kezzy?
Kind of. I can kind of hear you.
Maybe I should just type my question into the chat. Should I do that? Okay.
That also works. I'm happy to read it out.
Thank you.
In the meantime, if the person in the room wouldn't mind typing it out in the chat, we can maybe move on to another question, which was Martin's question of, I'm surprised that exception handling didn't pose conceptual difficulties. That was surprising. I agree that was a surprising result. Using conditionals as scaffolding for exception handling seems problematic. How was control flow covered in the course, and kind of what is that interplay between exceptions and conditionals?
Yeah, so I totally agree. I was also really surprised by that result, but the way exceptions were introduced in the class was extremely basic. It was essentially just a try-catch block, and if something happened, you would just print out another message saying there was whatever the instructor wanted to do to print out is essentially what they would do. They only got as far as try-catch blocks, and they had one exception class. So it was almost easier for them, because prior to that, they had been working with multiple classes. When they saw interfaces, they were working with like 3 or 4 at a time. But when they were just working with one extra class, perhaps that might have felt easier. And also because all they were taught was the try-catch, it was very, very basic.
I see. I think I understand it's probably the question how complex the try is, because the try can give rise to arbitrary function calls within function calls and so on and so on, right?
Yeah, there was nothing like that. There was no
Got
of like nested function calling or anything like that.
Yeah.
Great. I think Jeremy's question next. Is that the one that was typed in from the room? Great. So in computational thinking, there are lots of different elements, of which abstraction is only one. Others include decomposition and recursion, for instance. Is abstraction more difficult or more important than the other elements of computational thinking? Do you have thoughts?
Oh, I love this question. So I was able to give a kind of a bit of a talk to another class about computational thinking, and I actually left abstraction out completely. I just talked about decomposition and recursion and those things, just because um, I think decomposition is definitely like it's a part of abstraction for sure to an extent, but the focus of this course was very heavily on abstract data types. So things like recursion were not heavily focused on. It was about a week long that they learned about recursion. So if the class had more emphasis on it, I would definitely have included that and maybe made it more of a computational thinking umbrella where abstraction was only a part of it. As to whether abstraction is more difficult, I'm not sure. I'm not sure I can answer that question confidently. I think maybe that's something, maybe room for future work for sure, to see what students are struggling with under that computational thinking umbrella. But all I can confirm is that abstraction seems to be a source of difficulty for students, not that it's more or less difficult than decomposition or recursion.
Great, thanks. I think we're reaching the end of this session, so I think we'll thank our speaker one more time.